so day 3, we're going to go through this fairly quickly. Hopefully you've been able to hit some of it during the Nearpod. We'll hit the themes. Hopefully you weren't able to catch on the Nearpod. Basically, relative rates of dissolution. I call this the Kool-Aid rules. I think I already talked to you about Kool-Aid rules, haven't I? When we did Kool-Aid. So to make Kool-Aid dissolve and get better faster, use small crystals. If we use powdered sugar instead of regular sugar, it would dissolve a lot faster. If we heat the water up, it's going to dissolve faster. If we stir it, it's going to dissolve faster. So those are the Kool-Aid rules. Just remember they have to do with dissolution, meaning putting it into solution. Okay? So grinding, stirring, and heating. I'm not going to spend a lot more time on that. Okay? So those are dissolution. We have different ways that we can talk about solubility. We have an unsaturated solution. That means I can dissolve more into it. Saturated solution means I've dissolved as much at that temperature as I can dissolve. And I'll end up getting something down at the bottom. It won't go in unless I heat it up. Supersaturated, I've heated the solution up. Now that stuff's dissolved and I've cooled it back down and it hasn't come out of solution. That's usually how we make candies. Okay? So you need to know how to label this. Again, saturated, unsaturated. Were you able to see this video? Okay, this one. Hopefully, oh, come on.
Isn't it on the next slide?
Is it? Ah, okay. Whoops, maybe. It doesn't want to go. All right, this is sort of fun. You can actually make this at home by putting vinegar and baking soda together, about a liter of vinegar with about a teaspoon of baking soda, dissolving it and heating it up. And just pouring it in there and it'll start to crystallize. If you ever have one of those hot packs, come on! And it clicks. Come on! And it starts to solidify. Come on! Come on! Hot up. Come on! Come on!
Put your palms together now!
Come on!
Come on! Come on!
So if you touch that would have
Come on! 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 Come on!
touched it, it would pop.
1, 2, 3, 4.
So it's sort of cool. If you're patient, you get it done at home by like baking soda vinegar, about a liter of vinegar, about a teaspoon of baking soda, and heat it up.
Say ooh, la la, say so. Come on, 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 say
Find a
ooh,
lot of these
la
out
la,
online.
say so. Come on, say ooh, la la, say so. Come on.
Come on! Come on! Come on! Come on!
1, 2, 3, 4.
Suicide! 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 To the beat end! Suicide! 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 To the beat end! Suicide!
All right, so we're going to go forward here, maybe. There we go. So we can do it in lab too. Just touching it will start it to go. You can put one piece of salt in there and it starts to follow that path and starts to crystallize out, which is cool to watch. It's called a seed crystal, or you can actually scratch the side of the flask and it will start. Just the vibration will set it off, which is sort of cool. So in the beaker below, we've got a beaker containing nickel 2 nitrate. We're going to sketch the particle view of what's going on. So up here in solution, remember that nickel to nitrate was separated into nickel +2 and nitrate with a -1 charge, right? How's the water going to go around that? Do you remember? Okay, remember that water has the oxygen, which is negative, and the hydrogens out here, which are positive, right? So what side of water is going to be attracted to the nickel? The oxygen side or the hydrogen side? Oxygen side, right. So we're going to have water surrounding nickel looking like this with the hydrogens on the outside. So as a group hanging around here, it'll look like an overall positive group because the water arranges itself so the positives are on the outside. Okay? What about the nitrate group? What's going to be attracted to the nitrate group? The hydrogen side or the oxygen side? The hydrogen side, yes. So we're going to have hydrogens coming in here. The oxygen's going to be left on the outside. Hydrogen's in here. Oxygen on the outside. Hydrogen's here. Oxygen's on the outside. Hydrogen's here. Oxygen on the outside. And it's surrounded so that it actually has a negative on the outside. So nitrate again looks like it's negative. What was this called? Do you remember what this was called? It's not dissolving, it's not a chemical reaction. What was it called? It's not salvation, it's solvation. Okay, so just remember, it's sort of like salvation, but not really. It's solvation. So they're not really interacting, they're interacting, but they're not chemically reacting. Okay? All right, so down here, when we got the solid, we had the solid where it was set up nickel +2, nitrate -3, and then we might have a nickel +2 that's sort of attracted to the nitrate because we have two nitrates over here, one up here. Okay, and we have this nickel and maybe a nitrate down here and one over here. Okay, this is my solid, so it's sort of set up so it's in a pattern. Okay, it's in a grid because it's an ionic compound. So it's positive, negative, positive, negative. And what happens is the oxygen and the water come in, and what's attracted to the nitrates again? Hydrogen. So hydrogens come in here like this and start to pull it out. So the hydrogens would come in like this and start to pull it out. And I didn't put a nickel up here. So the oxygen on this side would start coming in and start to pull this out. And we put some dotted lines so I can see that they're starting to pull it out. Okay, and they're starting to move them out, start to attract them away from that crystal. So where we have the solid right here, along this line is where the water attacks and starts to pull that crystal apart, starts to solvate it. Okay, so this is the particle view. So a lot of the AP tests, a lot of the ACT stuff wants you to be able to look at particle view, what's really going on inside the solution. Okay, so you got to sort of visualize it in your head. Everybody okay with this now? All right. So that was the end of that day. Concentration, why is it important? What does it mean when something's concentrated? You go to the store and it says concentrated orange juice. What does that mean? Sean, what does it mean?
I don't know, I forgot it.
So if you go get a thing of orange juice and it's in the freezer section, it says concentrated. You take it home, what do you have to do before you drink it?
Shake it.
You have to dilute it with water.
Well,
If it's in the frozen,
okay.
section.
Oh, I thought you were talking about like.
I was like, okay, shake it, all right. It's okay. Sean, wake up. Okay. All right.
I don't like that frozen juice.
You don't like the frozen juice. Okay, you like the fresh stuff. Got it.
Yes, ma'am.
All right. So concentrated means it's been made so it's more concentrated. So concentrated. Okay. List some everyday items that are packaged and concentrated form. I told you one, orange juice. Got any others?
Strawberries.
What? Kool-Aid, yep. Strawberries.
Yeah, like the frozen ones.
I don't know about that.
No?
You don't add water to them, right?
I mean, if you want them to unthaw, yeah. I don't know, it's concentrated, right?
Oh my goodness. Okay, so if it's concentrated, it has more stuff in it. I have to dilute it to be able to use it. So think of something like that. What do I have to dilute to make it something I can use?
Yeah, lemonade like that.
Okay, so the orange juice, lemonade, Kool-Aid we talked about. Come on. Miracle Grow.
What?
So like fertilizer, you don't want to put it right on your plants because what happens if you put it right on it? It burns them, they die. Okay? Any of here's your strawberry stuff, but it's the stuff you put in your drink, you know, or flavoring. You don't want to drink that vanilla or strawberry flavoring by itself. You want to dilute it a little bit.
drink that stuff raw.
You drink that stuff raw? Ah! Okay. Or eating like bouillon cubes by themselves, you want to dilute them.
That's gross.
Okay, that's gross. So this is me telling you I am sick and I'll be getting back to you on Thursday. So here's Thursday. Parts per 100. Now, this is where everybody goes, this is so hard. Parts per million, parts per billion, parts per 100. This is just really, I don't get this. You guys know how to find a percent on the test, right? Doesn't matter what the test is out of, right? If you have 23 out of it on a test that was out of 35, can you find your percent? Okay, find it for me. What is it? 25 out of 30, what did I say? 25 out of 30, 23 out of 35, there we go. What's my percent? What's my percent? Use a calculator, I got them.
66%.
66%. How'd you do it?
I divided the number that you got by the number total,
Okay, and?
multiplied it by 100.
So when we work with water, when we work with air, instead of saying percent, we say parts per 100, or parts per million, or parts per 1,000, or parts per billion. What do you think the difference is to go between those? What you multiply it by. So part per million, I would multiply it instead of by 100, I'd multiply it by 10 to the 6th. Parts per billion, I'd times it by 10 to the 9th. Parts per 1,000, I'd times it by 1,000. Okay? So that's pretty easy. All right? So think of it like that. Percent is just parts over 100. Okay? And you times it by 100. That's parts per 100. Parts per million, how many parts per million parts of a solution? Parts per billion, how many parts per billion parts of a solution? We're going to be using these. We're going to be using them a lot. You got to know them. Okay, now this is where it comes into, this is chemistry you're going to be using as a consumer. Because yearly, your city's supposed to report to you what's in your water. Okay? And guess what? They have a lot of people that have no idea what's going on. And so they report it and they say, yeah, ppm, ppb, pph, it's all the same. No. If there's 1 part per 100 of lead in my water, I'm really concerned. Okay? The H sort of looks like a B. So most people will just gloss over it. You need to know what it is. Okay? So know what you're doing here. If you don't know what million is, it's 10 to the 6th. If you don't know what billion is, it's 10 to the 9th. You're going to be able to find these for me. Be able to write, tell me what this is. Okay? All right. So how to visualize this? Were you able to watch this? Yeah? No? Okay, we'll watch it really quickly here. I know some of you were able to
is a unit of measurement. Parts per million counts the number of units of one substance per 1 million units of another. It can measure concentrations when a small amount makes a big difference. For example, a concentration of just 35 ppm of carbon monoxide in the air is poisonous to us. We encounter measurements like this pretty often, but because it's hard to conceptualize really large numbers, it's difficult to wrap our brain around what 1 part per million really means. So here are 9 helpful ways to visualize it. If you had 11,363 pianos worth of piano keys, one of those keys would be about 1 part per million. So would a single granule of sugar among 273 sugar cubes. 1 second in 11.5 days. Or 4 dots in the painting A Sunday Afternoon on the Island of Le Grand Jatte. Your bathtub's capacity is about 60 gallons, so 7 drops of ink would be 1 part per million. The English version of the Harry Potter series has 1,084,170 words, which makes hippogriff on page 221 of The Prisoner of Azkaban a little less than 1 part per million. A million kernels of corn is about 1,250 ears, so 1 kernel in that truckload would be 1 part per million. There are 10 million bricks in the Empire State Building, so 1 part per million would be a pile of just 10. And finally, 100 people worked together to animate this video. Collectively, they have about 10 million hairs on their heads. Pluck 10 of those hairs, and you have 1 in a million.
It makes me laugh. Okay, let's go on here. So, describe part per billion. There was several different ways I gave you. There's a few up here. If a record or CD sells 1 million copies, then 1 single record is 1 part per million. You can sort of see the other ideas there. So, let's see what we can do here. What is the percent NaCl in a solution made by this, adding this to this? Okay. So, what is the percent? What do I need to do? I have to be a little careful here because I'm adding this to this, so I'm going to take the 43 divided by the 157 plus the 43 because I've got to have the total mass. So it's not like I had a test score. I've got to have the total on the bottom, and then I'm going to times it by 100. Okay, and that would give me parts per 100 or percent. And we got that? 21.5, all right. Okay, how many grams of AgCl are needed to mix 500 grams of 150 parts per million solution? So, that gave me the total mass. I don't know how much I need. I'm going to put X on the top, 500 on the bottom. What am I timesing it by to get parts per million? 10 to the 6, good. And it equals 150 parts per million. Solve for X. So what do I need to do to get to X? I'm going to go. Okay, so 150 times 500 and then divide by a million, right? Okay, let's get it. One more time.
1075.
0.75. Okay, and that's how many grams I need, not very many. Now, the next one says, what is the concentration of H or Ag plus ions in the previous solution? If I look at this, what does this break down to in solution? Doesn't it break down into Ag plus and Cl minus? We're going to assume it totally breaks up because chlorines are, for the most part, soluble, even though here, silver, it's not very soluble. We're going to assume that they're both split up. I get 1 for every one of these, right? This is a trick question. It's the same. Now, if I had done magnesium chloride, if it was magnesium chloride instead of silver chloride, then I would get 1 magnesium plus 2 ion and 2 chlorine ions. So if I had asked for chlorine, then I would have doubled that. Okay? I love you. Come back. It's stinky. Okay, so really? All right, well, it must have been the end of that one. So let's go. That was part 1. We're done with that. We'll go to part 2. Come on. It really doesn't want to play with me nicely right now. All right, so we got a little video here at the very first. We already watched that one. So we're going to go on to the next one. How many like Big Bang Theory? I like to watch it. So this is a little excerpt of it, and I thought it was pretty funny, and I don't know if you were able to see it or not.
Doctor said I should be out of surgery by 10.
Okay. And Sheldon really believes we're at a public swimming pool?
He was so busy figuring out how many parts per million of urine we'd be floating around in, he didn't even question it.
18 parts per million. And he's still doing it.
Don't worry about that. I'm happy to take you to work.
Well, thank you. Yeah. And Leonard never lets me have French toast sticks in the car. I can't have syrupy fingers, but he can do the backstroke in a toilet bowl.
It's nice they're getting exercise.
Although now that I think about it, Leonard would never go swimming in public without his swim shirt.
I'm sure he brought it.
Oh, but last year at Magic Mountain, he got such a bad sunburn, we had to cut him out of it.
You probably got a new one. Finish your breakfast. Look, there's an entire section of my dashboard that doesn't have any syrup on it.
You're acting odd. Why?
I'm odd all the time. Everyone knows that. Just last night, I tried to see how many fava beans I could fit in my mouth.
Tell me the truth.
28.
Come on.
56.
Amy, what's going on?
All right. Don't get upset, but an earlier appointment opened up for Leonard, and he's getting the surgery right now.
I see. Take me to Leonard.
Just go to work. He'll be fine.
Amy, he's my best friend. And if you don't take me, I'm going there anyway.
Fine. It's sweet that you care about him so much.
I do. And I wouldn't be able to forgive myself if something happened to him and I wasn't at his bedside to say I told you so.
Love it. So that's how some people think, right? Pretty gross. So in the episode of The Big Bang Theory, Sheldon freaked out about peeing in the pool. Why? Given that there are 18 parts per million of urine in an Olympic-sized swimming pool, how many milliliters is that if the swimming pool contains that many liters of water? Okay, so how do we figure this out? Same way we did before, right?
Oh, wouldn't you subtract that?
So we don't know how much, right? But we know that there's 2,000 or 2,500,000 liters. We're going to times that by, what was it? Parts per million. So what do I times it by?
18.
10 to the 6th. And I get 18, right? So what do we need to do to find that out?
Don't you need to divide that?
Okay, so x is going to equal 18 times 2,500,000 divided by 10 to the 6th. What do we get?
45.
How many?
45. I did that right.
45 liters of pee.
Ew.
So now you know why I was freaking out.
Oh, have you like seen the thing like on Grown Ups too? I think it's on Grown Ups, but like they have like the blue chlorine whenever like when yeah.
Now that summer's winding down and you've already spent lots of time in the water, I want to show you now how to figure out how much pee is in any pool. There's actually a lot of misinformation on the topic of pee in pools, so I'm going to do some experiments on my own, along with some clever science people in foreign lands, and spoiler alert, some of the results are good news and some aren't. So let's jump right in. So this first experiment is to determine how much pee is in an actual sample of pool water using an ingenious method. So I got 2 samples from my friend's community pool where lots of people swim, one from the pool and one from the spa. And then 2 samples from a friend's backyard, again, one from the pool and one from the spa. I also collected samples from the source water at each location as a control, and I'll explain why in a minute. Now that I have my samples, I needed to quickly get to my scientist friend Lindsay in Canada, but lucky for me, I knew a shortcut. We are now in the lab of the University of Alberta, and this is Lindsay Blackstock, and she is basically a genius. So you are going to help me determine how much pee is in these samples, because we know people pee in the pool.
Yes, we have strong evidence that people do pee in the pool. So we're going to try to find a way that we can measure that pee without actually measuring pee. I'm going to apply my new strategy based on the amount of artificial sweetener that's in the pool. We know artificial sweeteners don't come from anywhere except for urine. So that's the only logical source for them. If we find them in the pool and we know how much artificial sweetener is in the average person's pee,
right,
and then using that, we can estimate how much pee is in the pool.
Got it.
So we're going to take this sample, we're going to bring it over to our sample prep bench.
Okay.
We're going to filter it, transfer it into some special vials, into this instrument, which is a liquid chromatography system.
Of course.
So this instrument is going to concentrate our sample before it passes it on over to the second instrument, which is a mass spectrometer. And the mass spectrometer is able to detect the individual little artificial sweetener molecules one by one.
Love it. Let's get to work.
Bring it on over there.
Before we run the samples, let me explain why I find Lindsay the scientist's solutions so brilliant. You can actually take a sample of pool water and directly measure the amount of urea in there. But the problem with that is humans also excrete urea through things like sweat, which is also very common in a pool. So you can't tell how much of that urea actually came from pee. To get around that, she looked at the amount of a certain artificial sweetener in the sample called asulfame potassium, which is really common in food products such as these, oh, and also all of these. So pretty much everything. The reason drinks like these are 0 calories is because you taste the asulfame potassium sweetener, but the chemical compounds aren't broken down at all by your body. So more than 99% is passed through in your pee within 24 hours. And therefore, the only reason this would be in the pool is if it passed through a person first. And just to be sure, we measured the source water at both locations, because sometimes trace amounts of the sweetener can be found in the water supply. And if so, we just subtract that from the results. And I love this, because we've all wondered how much pee is in a specific pool. But Lindsay figured out a really clever way to use proven science to actually answer the question. The mass spectrometer takes about an hour to get results, so while we were waiting, Lindsay told me something that really surprised me. Chlorine in pools is obviously really helpful because it breaks down harmful bacteria, viruses, and microbes that would be harmful or even potentially deadly to humans. However, there is one big downside, and that is it reacts with urine to create a byproduct called trichloramine.
So trichloramine is what's responsible for that chlorine smell that you might get when you enter into an indoor swimming facility. It's
But if
also
I just smell chlorine, like straight out of the bottle, it kind of has that chlorine-y smell to it.
yeah, but the smell that you smell in a pool is trichloramine. Like this is the compound responsible for that characteristic swimming pool smell.
And if I look skeptical here, it's only because I was. So I devised an experiment of my own to see if this was really true. For the experiment, I got 2 5-gallon buckets and filled them with pure water. Then I added 4 times the recommended concentration of chlorine for that volume of water to both buckets. And then only in the bucket labeled B, I added just a little bit of P. And then I let it sit for a couple days. All right, so it's been 3 days, so this is the moment of truth. So the first thing I notice is visually they look the same. You can't tell one bucket from the other as far as color of water goes. So I'm gonna start and smell this one first. So that doesn't smell like anything. That smells just like water, even though this has 4 times the recommended concentration of chlorine for this volume, which makes me nervous to smell this one. What? That is crazy. This smells like a pool, even though the only difference between these two is this has a little bit of pee in it. This is a nostalgic smell. This smells like summers and vacationing at hotels with pools and water parks. Turns out it was just pee. So if trichloramine, which again is what is produced when pee reacts with chlorine, was just that classic pool smell, that's not that big of a deal. But the problem is, it's kind of bad news for both your lungs and your eyes. When your eyes are really red after swimming for a while, that's actually because of the trichloramine from the pee, not the chlorine. Trichloramine also causes things like asthma. In fact, studies show asthma is more likely to occur among elite swimmers than any other high-level athlete. Which now makes sense because Michael Phelps admitted to always peeing in the pool, and he says all his buddies do too. So be cool and don't pee in the pool. Now let's go see Lindsay's results. In Lindsay's research, she sampled 20 public swimming pools and 10 public hot tubs. The average concentration of sweetener for the pools was 470 nanograms per liter, and for the hot tubs was 2,247. So after running all of my samples, we found that here in my friend's backyard pool, they had a concentration of artificial sweetener of 69 nanograms per liter, which equates to just under a gallon of pee, which is actually much lower than the average, but that makes sense because this would see much less use than a public pool. Their spa had a higher concentration than the pool at 103, but since a spa contains much less volume, that equates to about this much pee. So far, not bad. And then in this public community pool, we had 27 nanograms per liter of artificial sweetener concentration, which for this volume is again a little bit less than a gallon. And then the spa was higher at a concentration of 335, which is about this much for the volume of the spa. So the concentration of artificial sweetener in this pool and spa is much, much lower than the averages Lindsay saw in the 30 samples she collected, which leads me to believe that the water has been completely replaced recently, which happens from time to time for various reasons. If this pool had the average concentrations reported by Lindsay, for these volumes, we would expect to see over a gallon of pee in the hot tub and about 13 gallons in the pool. If you want an estimate of the pee in your own pool, I came up with a simple equation after talking with Professor Ernest Blatchley of Purdue University, who mentioned that studies have found that swimmers introduce between 25 and 80 milliliters of urine per swim session. So you take the average number of swimmers that were in your pool per day during the summer, and then you multiply that by 1.2. That's how many gallons of pee are in your pool at the end of the summer. And if you think your friends and neighbors pee more than average, use 2 as the multiplier. And if you think they are more on the courteous side of the range, use 1/2 as the multiplier. As a general rule of thumb though, public pools about this size will contain approximately 13 gallons of pee, and Olympic pools will contain, brace yourself, over 130 gallons. There are some caveats to these generalizations, so check out the links in the video description for published papers from both scientist Lindsay and Professor Blatchley. So in conclusion, what does this all mean? Like, is this something to be grossed out about? For starters, let me just say pee is generally considered to be sterile, meaning it's free from bacteria and any living things. You could totally drink the stuff and not get sick. In fact, in some cultures, that's totally a thing.
You drink the grandson's pee and it's gonna help you.
Additionally, urine is made of 95% water and just 5% of dissolved solids like the urea stuff we've been talking about. The fact that pee is so dilute at 95% pure water is in part, disappointingly, why it's really hard to make a chemical you could add to any pool that will magically turn blue if someone pees in it. Having said that, I suppose it's still a little gross knowing you're swimming in even just a small amount of pee, but I feel the benefits to your happiness and well-being that can come from swimming far outweigh any sort of gross factor or minor health risks. I guess at the end of the day, my advice would be to be cool and don't be in the pool. And then at that point,
Just keep swimming, just keep swimming, just keep swimming, swimming, swimming.
Just maybe take a shower when you're done.
speaking of
Okay, so let's look at some more. I really like that because it sticks in your head. Okay, so we also use water parts per million for air too. So given that there is one blue marble in a total of that many marbles, what's the parts per billion? What would I do to do this? Help me set it up. What do I need to do? How do I find parts per billion? Come on, Sean, help me. What do I need to do? You know how to do a test, right? Find your percent on a test. How do I find this?
Subtract.
No subtracting.
Divide.
I got 1 out of 45, blah, 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 blah.
Well, if you got 1 out of 45, then you just basically failed on the test.
Yeah, I did. I really failed on this one. So,
Oh, yeah, if there's that many questions, holy what?
okay, what am I timesing it by?
100? Or, oh, a billion.
A billion. What's a billion? 10 to the 9. And I'm going to find out what it is. So really quickly, throw that in your calculator and tell me what it is.
Well, that's a really small number is what it is.
You sure?
What I got, yeah. If I did that wrong, then that sucks.
What do we get? Just keep swimming.
Exactly.
What do we get? You want to do the bottom one too, so if you want to get a head start on that, you just set it up.
Yeah, it's still a pretty small number.
Okay, what is it?
0.40 and 5 twos.
4 zeros, 1, 2, 3, 4, and
5 twos.
5 twos. That makes things always easy. Okay, what about the bottom one?
I forgot on that part.
Parts per billion, so that's really small, right? What we got for the next one? John, you should be writing this down. You have to turn it in. Dude. I do get credit for notes. So, and we upload them online. I'm sorry, I forgot to tell you that. Okay, so what do we get? Anybody got this last one?
Point 0.00000007.
How many zeros? 1, 2.
I think it's 3.
I got 8, yes. Alright. Okay, so we should be able to find stuff like this. Parts per million probably is not a good read for this because I got way too many zeros. So I would probably go parts per billion or parts per trillion instead. Okay? Because that's really small. Alright? Now, we're going to do this next time. We'll start with the water quality activity next time. And then we'll do our dilution thing next time also. Just remind me that this is where we need to start for me. If you put a little star for me or something there, so that I remember where we're going, because it'll be for another weekend. All right, if you need extra help, don't forget tutoring tonight. It'll be in Mrs. Sultry's room. So if you're a little behind, come on in and get some help. All right? Huh? And don't pee in the pool, that's right. You're in the pool so often. just wash off of it.
Yeah. We're in the pool Monday through Friday, 5:30 to 7.
Nope. Doggy paddle's the only thing.
Yeah.
That's a lot.
Just like the 36.
And when you get out, you'll be able to go back and look at the other lecture. Just this real quick.